This is lecture number 2, in chapter 5 about power distribution cables. I will first continue presenting short circuit current calculation methods, that I have started in the previous lecture. I will remind you about the per unit system, which is important and used in most of power system analyses. The per unit fault calculations is a method, whereby system impedances and quantities are normalized to a common base, across different voltage levels. By removing the impact of varying voltages, the necessary calculations are simplified. To use the per unit method, we normalize all the system impedances and admittances within the network under consideration to a common base. These normalized impedances are known as per unit impedances. Any per unit impedance will have the same value on both the primary and secondary of a transformer and is independent of voltage level. A network of per unit impedances can then be solved using standard network analysis, and fault current level can be readily determined, as the ratio of the fault voltage over the total fault impedance. In applying the per unit method, the first step is to select an arbitrary base power, S base, and base voltage, V base. Having selected a base power and voltage, the base per unit values of current and impedance can be calculated, for a single-phase or three-phase system, as given by these equations. Sometimes, per unit values are available for a given base voltage, but the problem being solved is using a different base voltage. In this instance, it is possible to convert the unit as follows. If we denote the given values in the old base system by old, and the new values in the new base system by new, we can calculate the per unit impedance in the new base system using this equation. Fault calculation problems typically deal with power sources, generators, transformers, and system impedances. Per unit values for these elements can be quickly derived as follows. Source impedance is determined based on the knowledge of source MVA, during fault at the main bus. This value is usually provided by the utility, or can be determined using a power system analysis software, if the network is modeled, and short circuit analysis at this specific bus is conducted. So, the per unit source impedance is calculated as the ratio of the base MVA over the source fault MVA. The generator impedance is usually provided by the manufacturer in %. To determine the per unit generator impedance on the common base, we shall divide the common base MVA by the transformer rated MVA, and multiply it by the given % generator impedance. Similarly, transformer's impedance is usually provided by the manufacturer in %. So, we can apply the same formula as for the generator case, to find the equivalent per unit transformer impedance in the common base. For line impedances, they are usually given in ohms. To convert them into per unit, we need to divide them by the base impedance. Or we can directly find the per unit impedance by dividing the base MVA by the square of the base voltage in kilovolts, and multiply it by the actual line impedance in ohms. Let's work on a simple example. We consider a system of source impedance 4.48 ohms, connected to a 20 MVA step-down transformer, from 11 kV to 0.4 kV, with 6% impedance. And we want to find the fault current level at the transformer secondary. We start by defining the common base power. Since we have only one element, which is the transformer that is rated at 20 MVA, we can take S base equal to 20 MVA. Then, we can calculate the base currents in two different voltage bases, 11 kV at the primary of the transformer. and 0.4 kV at the secondary of the transformer. The base impedance at the 11 kV side is calculated as shown here. We need this base impedance on the 11 kV side, in order to convert the source impedance into per unit. The per unit source impedance is therefore calculated as the ratio of the actual value over the base value, that is 4.48 divided by 6.05, that equals 0.74 per unit. The transformer per unit impedance is calculated using this equation, that yields a value of 0.06 per unit. Since the source and transformer impedances are connected in series, the resultant total fault impedance is the sum of these two impedances, that yields a total fault impedance of 0.8 per unit. So, the total fault current is calculated as the ratio of the voltage over the total fault impedance, that equals 1 over 0.8, equals 1.25 per unit. The fault current in kiloamps is determined by multiplying the per unit value the base current value at the secondary of the transformer, that is 1.25 times 28.87, which equals 36.08 kiloamps. We can also use the power relations and calculate the per unit fault current as shown here. As you can notice, the ratio of the fault MVA over the base MVA equals the per unit fault current, which equals also the inverse of the per unit fault impedance. The fault MVA at point A is calculated as the ratio of base MVA over the per unit fault impedance, that equals 25 MVA. Then, from the fault MVA, we can deduce the fault current, by dividing the fault MVA by square root 3 times the baseline voltage at the secondary of the transformer. This yields a fault current value of 36.08 kiloamps. That is exactly the same value as the previously calculated one. Let's consider a more general example. We now know that, per unit analysis can be used to easily calculate system three-phase fault levels, and the current distributions. To gain a better understanding, it is worth running through the typical steps required to solve a more general fault calculation problem. Given this system's single-line diagram, I will show how to construct and simplify its equivalent per unit impedance diagram. The fault level at the point under consideration is given by this relation, where ZPU is the total per unit impedance between the source and the fault. So, we have the source impedance that links to both transformers that are connected in parallel, as shown in this circuit diagram. We can convert this circuit into its equivalent one, that is shown here. So, the total fault impedance is calculated as the sum of these two impedances. Total fault MVA is calculated as the ratio of base MVA divided by total fault impedance. Fault flow through parallel branches is given by the ratio of impedances. Having calculated the fault flow in each branch, it is then relatively simple to find the current distribution using this equation. Having calculated the fault flow in each branch, it is then relatively simple to find the current distribution using this equation. Let's apply this general example approach to a practical one. We consider the power distribution system shown in this figure. We want to calculate the three-phase symmetrical short circuit current, at point A on the 11 kV network. We shall consider the following cable actual impedances. This is the linear impedance of the 33 kV cable with 240 mm² cross-section area. And this is the linear impedance of the 11 kV cable with 300 mm² cross-section area. And this is the linear impedance of the 11 kV cable with 200 mm² cross-section area. All per unit impedances will be calculated on 100 MVA base. We can select any value for the base power, but a value of 100 MVA is usually selected because it simplifies the calculation, when we multiply or divide by 100. Let's start with the calculation of the source impedance. We are given the source fault power of 700 MVA. We assume that the resistance component of the source impedance is negligible, so we consider that the impedance is equivalent to its reactance value only. So, the source per unit impedance is calculated using this equation, which yields a value of J0.143 per unit. Now, let's calculate the 33 kV cable impedance, in per unit. Positive sequence linear impedance, for the 33 kV, 240 mm² XLPE cable, is given by the cable manufacturer as shown here. Since the cable length is 7 km, then the total impedance is determined as shown here. Therefore, the per unit value of this impedance is calculated using this equation, which yields a value of 0.063 plus J0.07 per unit. Now, let's calculate the per unit impedance of the 33 to 11 kV step-down transformer. Since we are given the percent impedance, we can calculate the per unit impedance using this equation. Neglecting the transformer resistance, we can find that the per unit impedance of the transformer equals J1.43 per unit. Since there are two identical transformer cable branches in parallel, then the resultant total impedance is half of the sum of the cable and transformer impedances. That equals 0.0315 plus J0.75 per unit. That equals 0.0315 plus J0.75 per unit. Converting it into per unit, yields this value. Now, for the 1 km 11 kV cable of 200 mm² cross-section area with aluminum conductor, the total cable impedance is determined by this equation. And the corresponding per unit value is determined by this equation, that yields a value of 0.138 plus J0.275 per unit. The total 11 kV network impedance is then calculated by summing all the previously calculated per unit impedances of the two cables that are connected in series. The total fault impedance at fault point A is therefore calculated by summing the source, 33 kV network and 11 kV network impedances. So, the absolute value of the total fault impedance is 1.223 per unit. Since the ratio of the fault MVA over the base MVA equals the inverse of the per unit fault impedance, then, we can determine the fault MVA by dividing the base MVA by the fault impedance, which yields a value of 81.8 MVA. Finally, the fault current is calculated as the ratio of the fault MVA over square root 3 times the line base voltage. Now, let's consider the same power distribution system shown in this figure. In this case, a single phase to earth fault is assumed to occur at point B of the 11 kV busbar. The two transformers are assumed to have a YN-YND connection, with the star point solidly earthed. Let's calculate the short circuit current at point B on the 11 kV network. To start solving this problem, we should recall that this is an unsymmetrical fault, and that it requires symmetrical components analysis, in order to find the short circuit current. We have seen in the previous lecture, that for a line to ground fault, the three sequence currents are the same, and that they equal the phase voltage over the sum of the sequence impedances. Note that all parameters are taken in per unit. So to find the total fault current, we need to calculate first the total fault impedance, which is a function of the sequence impedances of each component of the network. We start with the source impedance, and we consider that the resistive component of the source impedance is negligible. It is also generally assumed that the positive and negative sequence impedances are equal to the three-phase fault source impedance. We know that the actual phase A current is related to its sequence currents by this equation. Since the three sequence currents are equal, then we can write that the actual current is 3 times the positive sequence current. That is equal to 3 times voltage UA, divided by the sum of the sequence impedances. That equals also UA divided by 1/3 of the sum of the impedances. Knowing that, the fault current IA equals the voltage UA, divided by the total fault impedance. Then, we can write that 1/3 of the sum of the sequence impedances is actually the equivalent total line to ground fault impedance. We will apply this formula to all calculations of network impedances. Applying it to the single-phase fault source impedance. And knowing that the fault impedance in per unit is actually the ratio of the base MVA over the fault MVA. We can write that this fault source impedance equals base MVA over source MVA fault. That is equal to J1.163 per unit. Note that we considered the resistive component of the source impedance negligible. So, we can calculate the zero sequence impedance of the fault source impedance, as shown by this equation, which yields a value of J3.203 per unit. Next, we will calculate the sequence impedances for the 33 kV cable. We usually consider that the positive and negative sequence impedances for cables are equal, unless otherwise specified, so the positive and negative sequence impedances for the 33 kV, 240 mm² XLPE cable are given by this equation. These values were already calculated during the previous example of the symmetrical fault case. The zero sequence linear impedance for this cable is given, in ohms per kilometers, by the manufacturer, as shown here. Since the cable length is 7 kilometers, we can calculate the total zero sequence cable impedance, by just multiplying the previous linear impedance by 7, so that we get it in ohms as shown here. The per unit value of the zero sequence cable impedance is calculated by dividing the previous value by the base impedance, that is 0.49 plus J0.0868 per unit. Now, let's calculate sequence impedances for the 33 to 11 kV step-down transformer. Similarly, we consider that the positive and negative sequences are equal to the symmetrical value found earlier. When the zero sequence impedance is not specified, we can assume that the zero sequence impedance value is 90% of the positive sequence one. When the zero sequence impedance is not specified by summing the 33 kV cable and transformer impedances is 90% the result of the positive sequence because we have two identical parallel branches. After calculating the total impedance for each sequence, we can calculate the total equivalent line to ground fault impedance, using the previously demonstrated formula as shown here. Now, we can calculate the total line to ground fault MVA at point B, using this equation. And the corresponding total line to ground fault current, is finally calculated using this equation. Notice how this current is much smaller than that obtained at point A under symmetrical fault. This is expected, because as I mentioned earlier, the three-phase symmetrical fault is usually the most severe one, and that is why it is usually used for short-circuit current calculation and cable sizing during the design of the distribution network. Cable riser is a specially allocated space for electrical wiring to rise up a building, in an orderly, organized, and safe way, mostly in a vertical fashion. Sometimes, they share the space together with telecom and IT cables, and occasionally even together with city water, water supplying sprinkler and fire protection systems, city gas, exhaust ducts etc., where the local building codes allow. This picture shows an example of how the cable riser looks like. This layout shows at the center of a building the different risers used for the different utilities. You have the electrical riser, designated by ELEC in this drawing, cable or television riser, designated by MATV, telecom riser, designated by TEL, dry riser, designated by DR, city water, designated by water, etc. This photo shows some devices being installed in the riser itself. Also, depending on the local building codes, the penetration between floors must be sealed with fire sealant, that prevents fire from spreading between floors. However, some others don't have a solid floor, and let you see through to other levels. This is convenient for tracing where wires go, and also easier for you to plan if you're adding new wires, so at a glance you can tell which cable tray or path is most convenient for you, to use without hitting some obstacle several floors up. The risers, and the wires within, have to be specially and carefully designed, to prevent fires from climbing the wires, and spreading to other floors. In the electrical wiring of buildings, a cable tray system is used to support insulated electric cables used for power distribution and communication. Cable trays are used as an alternative to open wiring or electrical conduit systems, and are commonly used for cable management in commercial and industrial construction. They are especially useful in situations where changes to a wiring system are anticipated, since new cables can be installed by laying them in the tray, instead of pulling them through a pipe. In large buildings, the type of distribution depends on the building type, dimension, the length of supply cables, and the loads. The distribution system can be divided into the vertical supply system, with rising mains. The horizontal supply, for power distribution at each floor level. In most cases of large buildings, a high voltage main supply and transformer substation is required. Normally high voltage switchgear and substation transformers are installed at ground floor, or basement. However, often there are appliances with large power demand installed on the top floors, such as converters and motors for lifts, air conditioning equipment and electric kitchens. As it is desirable to bring the high voltage supply as close as possible to the load centers, transformers are installed at the top floor, or if required, additional ones are installed on one of the intermediate floors. In such cases, transformers with non-inflammable insulation and cooling are used. The arrangement of the rising mains depends on the size and shape of the building, and suitable size of shafts for installing cables and bus ducts must be provided in coordination with the building architect. The vertical supply systems are implemented in several ways, some of which are single rising main, group supply, individual floor supply, ring main supply, double feed supply. In practice, all supply circuits presented above are used depending on the building type, size, load data, etc. Let's discuss one by one and start with the single rising main. This type is applied where high supply security is not important. It exhibits the following advantages. The different loads of individual floors are balanced out. Only a small main low voltage board is required. It is simple in construction and operation. While it has the following disadvantages. That is, its low supply security. Indeed, a fault in the rising mains affects all floors. Now, let's discuss the grouping supply type of risers. This type is applied in high-rise building with high load concentration. It has the following advantages. Smaller size for rising mains. And hence, easier mounting. Its main disadvantages are as follows. A fault in any rising mains affects several floors, implying relatively low security. Loads are balanced only within each group and not between the groups. And requires larger power distribution board. Individual floor supply types are applied in high-rise buildings, where stories are let separately, and metering is at central point at ground floor. They have the following advantages. In the case of a fault in a rising main, only one story is affected. Their disadvantages are as follows. Different loading of the individual floors cannot be balanced out. The rising main must be rated for the peak load of each floor. Uneconomical, since they require large number of cables, and the size of the rising main shaft is quite large. Finally, they require large low voltage distribution board with numerous circuits. The ring main supply is usually applied in large buildings when relatively higher security is required. Its advantages are as follows. Higher power supply security. Indeed, in the event of a fault, it is possible to switch off the faulty part and leave the majority of the building operational. A small low voltage distribution board is required. The differing loading of individual floor are balanced out. And it has smaller sizes for rising mains. Finally, the double feed supply is applied in large buildings with relatively large loads, at the top floors, such as lifts, kitchen, and air conditioning power unit. It has the following advantages. Higher power supply security. The differing loading of individual floors are balanced out. And smaller low voltage distribution board is required. This is the end of this lecture. I hope that it was clear and informative. Thank you for watching.